Okay, I want to talk about strain rate, stress, and viscosity, and I want to do that um, or through the context of mantle convection. And so let me just draw a little cartoon here for the mantle. This would be the core. This would be the surface where it's cold and it's hot down here. And this distance would be the thickness of the mantle, which I'll call L. And because it's hot down below, you'll have thermal expansion, and that'll cause buoyancy, and that'll cause upwelling, a thermal upwelling. So you'll get these broad upwelling zones, and of course, to conserve mass, you'll also have to have some counterflow, which would be the downwelling zones. And the upwelling zones will be hot, and they'll be the mid-ocean ridges, uh, spreading, plate spreading, and then the downwelling zones will be the colder areas where you have subduction. So let's talk about strain rate first. Um, that's this right here. Strain rate is a measure of the proportional deformation rates of any object. What I'm going to talk about is shear strain. And let's think of a sandwich here with peanut butter in between, right? This is a very thick peanut butter sandwich, so somewhat exaggerated. But what I'm going to do is shear the two sandwich planes here at a rate, say, given by some velocity, meters per second. And that's driven by a force, okay? If you were to, we call that the shear force. And the shear force, if you were to divide it by the surface area of the bread, peanut butter interface, that's A, then that would be the shear stress, which we'll call this sigma, okay? So when you do that, you might cause it to look something like this, right? And the velocity profile, if you were to look into here, the velocity profile in the peanut butter, this viscous fluid, right? If I plotted that velocity versus depth, okay, in my peanut butter, at the base right here, the velocity is 0. It's pinned to the, in the relative sense, to the lower piece of bread. And then further up, the velocity at the top will have to equal that of the top bread that you're pulling at a constant velocity. And you'll get something that looks like that. It's linear, okay? And so we define strain rate as something that's called this. It's epsilon with a dot on the top, which is actually dx dt, which is a velocity, divided by x. Now, epsilon by itself is dx over x. That would be the percentage change in distance. And when I take the time differential, then we have the change per unit time, and we put a dot over the epsilon right there to imply, to tell you that that is the strain rate. Now the strain rate here then is going to be equal to the velocity at the upper boundary there divided by this whole thickness of my peanut butter, which we'll call L. When Z equals L, this is L right there. So that's the strain rate, okay? Now, you might then ask yourself, let me do this. How much stress, force per unit area, shear stress, do you have to apply to deform this at a given strain rate or a given velocity, the upper boundary, right? And you might think that it will depend on what's in there. Is it peanut butter or is it jam or something else? And so you would expect that something much more viscous would be much more difficult to deform, and you would have to apply a higher shear stress to deform it at the same rate. Okay, so the reason why that controls the rate of deformation, that viscosity, we'll come back to that in a second, is that that's essentially telling you about how much what we call viscous dissipation is occurring within this layer, this viscous layer. That viscous dissipation you can think of as a frictional resistance. In this case, the friction is within the peanut butter. And so if you put a lubricating oil in there and the frictional resistance is low and the system is weak, and you can deform very rapidly for the same applied shear stress. So what you can do is usually in a system like this, you would look at a force balance, which is the sum of all forces is equal to mass. We do this all the time in terms of acceleration, right? And then that's equal to your applied force, okay? That thing right here is sigma times A, right? That's the applied force, minus some frictional force, okay? And what we want is to understand how friction behaves. And what we're going to do, make our assumption here in this little experiment that you might do in your kitchen, that maybe you can do it where it's viscous enough that as you slide it, you can do it at a constant rate, a constant deformation rate, constant strain rate, right? And so this term we can set to equal 0. So our applied force, sigma dot A, will then equal to the frictional force, okay? Now, from experiments, we can, you can do this in, again, your kitchen. We can look at how much, how stress varies with, or shear stress varies with strain rate. What you'll get is this, I'll put this as my shear stress, and I'll put this as the strain rate. You might go, well, if I don't apply any shear stress, then this is not going to move, right? So that's common sense, that's going to be there. Now, if I start to apply a shear stress, it will start to move. And the higher the stress, the faster it will move, the faster it will deform. There is a condition or a type of rheological property where that relationship is linear. We call this a Newtonian fluid, okay? Rocks, for example, even though they're solid, can behave rheologically as a Newtonian fluid. And if it's linear, then we'd have sigma is equal to epsilon dot multiplied by the slope of this line, which we'll call eta. Turns out this eta is viscosity, right? And that has units of pascals, seconds, right? The units of stress are pascals, units of strain rate, I forgot to talk about that, but this is meters per second, right? And this is meters. So strain rate has units of 1/seconds. And so all the units work out. So you can see here that the higher the viscosity, the higher the slope is here. So this would be high viscosity, right? The more stress you have to apply to get the same amount of deformation. In reality, there are materials that will, one, behave non-linearly. We'll call those non-Newtonian. They may become easier to deform when you get more strain, or they may become harder. And we'll talk about those properties later. There are also some materials where nothing deforms ductily until you reach some critical shear stress, and those things we call Bingham plastic fluids. But for now, let's keep it simple and look at Newtonian fluids. Now, this thing is essentially what we'll call a constitutive law, okay? That thing has depends essentially on experiments or observations. There's no way you can, well, I guess you could get that theoretically, but from first principles, but it really is something you get from experiments or calibrate from experiments. And that is how the system or how friction is manifested. So if I take this and put it into here, and I have essentially my applied shear stress here is then equal to eta epsilon dot, okay? And I've dropped the areas because I would have to multiply this side by area and they would cancel out, okay? So this would be for steady flow there. Okay, so this is a good equation to get to know, and hopefully you get a feel for what it means by some of these diagrams that I've drawn. Now what I want to do is take these concepts and apply them to the Earth. So let's look at epsilon dot for Earth, okay, or for the mantle. Remember, epsilon dot is V over L, and we can think of, say, plate tectonics. The upper plate is moving here at some velocity, let's say about 10 centimeters per year, okay? And that's acting over 3,000 kilometers. Well, if it's symmetric, there's convection there, maybe the length scale that over which shear is happening is about half that, 1,500 kilometers. We're just looking for order of magnitude, so it doesn't really matter. So we'll just take 1,000. So let's look at what possible strain rates might be, right? We take velocity divided by L. So the velocity would be 10 to the negative 1, that's 10 centimeters, right? Meters per year. I'm gonna do this in SI units. Obviously this 1 year is equal to 3 times 10 to the 7 seconds. That's a good number to remember. Now, we're going to divide by 10 to the 3 kilometers, right? That's the typical or characteristic length scale over which the deformation is occurring. 3,000, 2,000, it doesn't matter. I'm going to convert this to SI units, right? So that's, 10 to the 3 meters. You can see my kilometers cancel, my years cancel, my meters cancel, and then I'll get 1 over seconds. So what you get then is 10 to the negative 14 per second. So that's the average strain rate for mantle convection and plate tectonics here on Earth. As long as you know what the average plate velocities are, this is what you get. It has units of 1 over time. Now, what does this actually mean? Just to get you there. So if I have epsilon dot and go back to that equation that I wrote over there, that dx dt over x is epsilon dot, which is 10 to the negative 14 per second, right? Well, that is also dx over x, and we'll have dt here, and you can be epsilon dot dt dx over x right here. What I should do is, if I were to put I should put a negative here to describe the shortening that might happen in the vertical direction when you shear this. And anytime you see a differential divided by itself, or the variable itself, which is a fractional differential, you will get a equation that is exponential in time, and x is equal to x0 e to the negative epsilon dot t, right? And so this epsilon dot, if I were to put 1 over epsilon dot, has a units of time, so some characteristic time, right? And 10 to negative 14. If I flipped it over, okay, comes out to be about 3 times 10 to the 6 million years. What that means is with these deformation rates, it's going to take you about 1 million years before you can stretch this this thing by a factor of e, the exponential. That's about 3. So it's a long time that you have to wait, 1 million years. But those are plate tectonic time scales. Okay, so now what I want to do is talk about so what are the shear stresses that we're talking about in the mantle that causes plate tectonics or this sort of deformation. So again, we can go back to this equation here. And what I'm going to tell you, and we'll have to figure this out later, but is that if you take the viscosity of the mantle, right, to be, let's say, about 10 to the 18 pascals second, you're going to have to just accept this. And later we'll derive how you get this from observations. Then my shear stress would then be 10 to the 18, negative 18 Pascal seconds. Sorry, positive 18, right? 10 to 18 Pascal seconds. Just for context, the viscosity of like a liquid basalt lava might be about 1 Pascal second. So 10 to the 18 is very, very high. And then you multiply this by 10 to the negative 14 per seconds. That's the strain rate that we derived. And in the end, what you get here is about 10 to the 6 pascals, okay? And that is the shear stress that is needed to drive flow in the mantle, 10 to 6 pascals, okay? This is what we call a deviatoric stress, and that'll become clear in a second. And because what I want to do is place this 10 to the 6 pascals into context. So if you go down into the mantle over here, there's another quantity we can talk about, which is called lithostatic stress. This would be analogous to hydrostatic stress. If you were in a swimming pool at the bottom, that would be the pressure you feel in a bottom swimming pool on your ears. And that's just the weight of the overburden above you divided by the cross-sectional area on which it's acting. And that lithostatic stress, as we had shown before, is rho g, well, it's actually this, the integral of rho g dz, but for simplicity, rho, the density times gravity times the depth, okay? And it turns out, you get down to, I'll let you do the calculation yourself for a density of 3,000 kilograms per cubic meter, 10 meters per second squared. So if you get down to, say, 45 kilometers depth, we're talking about 1 or 10 to the 9 pascals, which is a gigapascal, 1 gigapascal. So lithostatic pressures in the Earth, unless you're way at very shallow depths, are on the order of gigapascals, 150 gigapascals when you get down to the transition zone, if I remember correctly. So the stress that's actually causing deformation is 10 to the 6, or a megapascal. So stress driving deformation is megapascals, 1, maybe slightly less, but the lithostatic is gigapascals. So, and so lithostatic, if you have lithostatic pressure, that cannot drive flow because there are no lateral pressure gradients in that sense, in that case. The only way you can drive flow is you have to have some pressure gradients, right, that cause a deviation from this lithostatic. And this is why this stress, which drives flow, is what we call deviatoric stress. Okay, so the key is it's very small. The amount of stress released in earthquakes is also very small. It's nothing like a gigapascal. And it doesn't take a lot to cause the mantle to flow. Now, of course, this megapascal is a lot more than the flow that would be needed, or the stress to drive flow in, say, a swimming pool. But let me go back to the swimming pool analogy. If you're in the swimming pool and you're at the bottom, you feel the hydrostatic pressure, which can be very large. But in the absence of any lateral pressure gradients, the water will not flow in the swimming pool. It'll be static, hence the word lithostatic. What causes flow within the swimming pool, or for that matter, an atmosphere, wind blowing in the atmosphere, is very, very small deviations from the hydrostatic pressure. And those are caused by changes in temperature that drive buoyancy driven flow. Okay. So this hopefully helps you put some numbers to the Earth. So 10 to the negative 14 per second is the strain rate for our planet, or the mantle and plate tectonics. And the types of stresses we're talking about are about a megapascal, maybe slightly less.